Welcome to the special colloquium. Today we have Professor Kip Thorne from Caltech give us a colloquium to the school. Kip has been a great figure of physics, theoretical physics and astrophysics over the past 50 years, making numerous contributions both through his own pioneering research, which opened new directions in theoretical physics and astrophysics, and also through mentoring of over 50 PhD students that have now gone on to become faculty members at leading institutions around the world and are leaders in this field, and also mentoring equally countless postdoctoral fellows. So when I was preparing for this introduction, I searched the internet and I found a very long Wikipedia article which very briefly summarized Kip's research achievements over the past half a century. I'm not going to do that. I'm not going to summarize all of his research achievements. I just want to highlight 2 points which are a bit personal for me. Also, these points don't feature in the Wikipedia article. So the first point is that Kip was one of the very few American physicists, American scientists who have been to the Soviet Union in the 60s and 70s and 80s, talking to leading Soviet scientists, in particular from the group of Yakov Borisovich Zeldovich. So this was an important bridge between the physics in the West and the Soviet physics, and Kip was perhaps the most important exponents for this bridge. I know of 2 major scientific results which came from that collaboration between Kip and Soviet scientists. The first result is development of fundamental theory of accretion disks in curved spacetime together with Igor Novikov and others. The second result is the lifelong collaboration between Kip and Vladimir Braginsky, which led to development of concepts such as standard quantum limit and quantum non-demolition measurements. These are concepts which are now widely used in modern quantum mechanics, modern quantum optics, modern quantum measurement theory. So this has all come out of collaboration between Kip's group and the group at Moscow State University. So this is one point which is interesting for me. Another point which is mentioned in Wikipedia is that Kip is one of the co-founders for LIGO experiment. LIGO is probably the most amazing experiment that has ever been built by mankind. Now, Wikipedia says that Kip has also contributed to the engineering study, engineering designs for LIGO Interferometer, and I don't think it's quite accurate. So I've seen some of the studies, and they're not really engineering. You know, this is very high-level theoretical physics calculations, which are basically using areas of classical physics such as statistical physics, elasticity theory, optics. So this is not quantum field theory, but nonetheless, this is very high-level theoretical physics that couldn't be done by engineers, I believe. So, and there are many other things, many other adventures that Kip has had. I'm not going to go into any more of this. So today, he is coming back to the core of his interest, his lifelong passion, which is dynamics of warped spacetimes.
Okay, so I would like to comment on Yuri's introduction, maybe by just saying that, yes, I've also read the Wikipedia article about me. 30% of it is wrong, and I will let you go dig in and try to figure out which 30%. But given that, I would guess that at least 30% of everything you read on the internet is wrong. But you're overly generous, Yuri, thank you. So let me begin with a few remarks about quiescent black holes. There are three aspects of the space-time curvature or warping around a quiescent black hole. There's the curvature of space, which we can visualize by imagine taking a slice, two-dimensional slice through the equator of the black hole. The geometry of that slice will be warped, it will not be flat. And if you take it out and put it in a flat space, it will have to bend down in order to accommodate it to the flat space if it's going to maintain its intrinsic geometry. And so it looks roughly like this in what we call an embedding diagram in general relativity. And it's described, this warping of space, by a spatial metric. I'm not going to be using general relativity, but this is just to remind those of you who know a little bit about it, that there's a three-space metric that describes that. Time is also warped by a black hole. Time slows, proper time is measured by physical clocks, slows as you go down near the horizon, slows to a halt at the horizon. Inside the horizon, time flows in a direction you would have thought was a spatial direction, which is downward. Another way to say that is that light cones point downward. So you cannot, because you're always constrained to move into the future light cone, you're dragged then in some sense by the forward flow of time down toward the center. This is all described by a single function, the so-called lapse function that appears in a space-time metric in this manner. And then there is the dragging of space into motion, or in more technical language, the dragging of inertial frames. But it really is physically like a dragging of space into motion. You can measure that motion, for example, using a laser gyroscope. And so space then is dragged around relative to the distant stars with some angular velocity omega that depends on how close you are to the horizon. And so you have the full space-time metric of those three pieces of the warped space-time. And then if you do an accurate depiction of this, that's what an accurate depiction is above the horizon. The horizon is down here. The white is the angular velocity of frame dragging or dragging of space into motion. If you go down near the horizon, you cannot avoid being dragged around with that angular velocity relative to the distant stars. There's the slowing of time. The split between yellow and red, time is flowing at 1/10 the rate it is far away. If you're down on Miller's planet and you're in interstellar, that slowing of time is a lot. 1 hour down there is 7 years far away. So you can have remarkable effects of this as depicted in Hollywood movies now as well as in physics. And then the warping of space. Now all of this is a warping without the presence of any matter whatsoever. You normally think that space-time curvature is produced by matter, but that's not really true. It's produced by the energy and the momentum and the distributions of energy and momentum that reside in the curved space-time. And in this case, that energy is contained in the warping itself. So the black hole is held together by nonlinear self-interaction. The energy that's tied up in the warping produces the warping, and it all holds together very, very stably. It's a very stable gravitational soliton in the language that one sometimes uses in nonlinear physics, a soliton. Now, back in 2006, when the story that I'm going to be describing really began, we understood a lot about quiescent black holes, more or less all there was to know about quiescent black holes, except for all the details, the interesting astrophysical details of how they interact with the external universe. And that's the guts of a lot of interesting astrophysics. But in terms of fundamental physics, in the absence of external matter, that was the Kerr metric that I was just depicting. Had we ever seen one? No. No, we had lots of indirect evidence that there were lots of them around. We'd never begun to measure the spin of any black hole. We could measure masses of candidate black holes by applying Kepler's laws to stuff moving around in orbit around them, but really no significant observational results. And as for wildly dynamic black holes, which you would get, for example, if two black holes collide, each of them spinning, each of them with the dragging of space into motion, like a tornado, but the tornado isn't whirling space, not whirling air. You imagine two black holes that collide. They're two tornadoes orbiting each other that collide. Each tornado then the two tornadoes produce a third, larger tornado, which is due to the motion of the energy of the two black holes going around. So two tornadoes enmeshed in a third, larger tornado. And you'd like to know what happens when those tornadoes are made from warped space and warped time. And that was the challenge in 2006. Did we understand anything? No. Had we observed anything? No. We understood a little bit. That's not entirely fair. We had Stephen Hawking's second law of black hole mechanics that said that the surface area of the final black hole after the merger would be bigger than the sum of the surface areas of the two black holes beforehand. But that's about all we knew. It was just about that. And so this problem actually goes back a lot earlier than that. Oh, let me comment on it in heuristic terms. It was as though we had only seen the surface of the ocean on a calm day. We had never seen it in a storm, and we had certainly never seen breaking ocean waves. And so the challenge then was to see warped space-time in a storm when time is oscillating in some wild manner, space is whirling in some wild manner, and this is all occurring as a result of nonlinear interactions of the warped space-time with itself. So that's the nonlinear dynamics of curved space-time. It involves some of the deepest issues in the nature of space and time, some of the most interesting astrophysical phenomena. And as I was about to say, this problem goes back a long ways. It goes back to my own PhD mentor, John Wheeler. This is a photograph I took of him lecturing about issues like this at the birthday party of Willie Fowler, who's sitting here, in Cambridge, England in 1968, as I recall. And Johnny Wheeler, he exhorted his students and his colleagues to go study and learn about what he called geometrodynamics, which is the nonlinear dynamics of curved space-time. And he posed a number of interesting problems that might be soluble. And we worked on some of these and made a little bit of progress, but not very much progress. The tools were just not there for us. And so by and large, we were great big failures at meeting Wheeler's challenge of the late 1960s. But today, we have two new tools for probing geometrodynamics that we didn't have in those days that are revolutionizing this subject. Numerical simulations on supercomputers and gravitational wave observations. And so that will take up most of my talk. And then at the end of the talk, I will talk about some other things that we have learned about other venues for geometrodynamics, just to fill out the picture of where we currently stand. So numerical simulations, they have been under development since the 1960s. That's a long time. 50 years of effort trying to formulate numerical relativity in a way that you could really solve Einstein's equations numerically on a computer for generic situations, which is what we're dealing with here. Big success has only come in the past 10 years. There's an interesting history of why it took so long. A big part of that history is that physicists did not go talk to mathematicians enough. There were deep issues in the mathematics that the physicists didn't understand. There were instabilities that were built analytically into the equations they were dealing with. They required reformulating the equations in new forms to get rid of those analytic instabilities. And this was just not understood for a very long time. That's just one example. In fact, in these last 10 years, numerical simulations have begun to teach us a lot about geometrodynamics. This is a slide that was created by an artist based on a sketch of mine when we first started planning LIGO in the early 1980s. Two black holes orbiting around each other, merging, colliding, and creating gravitational waves that will go propagating out. And this is our vision of it in the early 1980s, before any simulations had been done. We knew by then, from order of magnitude estimates already, that the power output in gravitational waves during the merger is 10,000 times higher than the luminosity of all the stars in the universe put together. Two black holes of any mass. If they're stellar mass black holes, the total energy that comes off will be a few percent of the stellar mass. And that power will be coming out for a very short period of time, a small fraction of a second. If it's two supermassive black holes, the total energy that will come out is a few percent of the total mass of those two supermassive black holes. The duration, however, of the waves is going to be hours or days. But no matter how big or small the black holes are, the luminosity, the power, is 10,000 universe luminosities. That's impressive. Okay? And there are no electromagnetic waves. It's all in gravitational waves. It's all gravitational waves. Except, and this is very, very important for LIGO, except for emission from disturbed accretion disks. And we hope that when we see in LIGO gravitational waves from mergers of black holes, we will see also emission from a disturbed accretion disk that's surrounding that pair of black holes. But from the black hole mergers, it's all gravitational waves. And the details of the collision of the geometrodynamics are encoded in the gravitational waves waveforms. And I'll talk about waveforms in a little more detail in a few minutes. But they're waveforms like what you might put from a sound wave on an oscilloscope. And so the challenge then is to do numerical simulations of black hole mergers, compute the gravitational waveforms, and then build a catalog both of waveforms and a dictionary that tells you when you see a waveform what is the nature of the pair of black holes that are producing that in preparation for advanced LIGO's observations. One of the early simulations was a simulation that I'm going to show you a picture, a film clip from by the SXS team. This is the project to simulate extreme space-times. It's a collaboration between Caltech and Cornell. Although I started LIGO, I hate working in big projects. And I stayed in it until it was sufficiently robust that I felt I wasn't needed anymore. And there were younger people, such as Yuri here and Eric and others here, who could do anything that I could do better. And then I got out as fast as I could. And I then put together a numerical relativity team at Caltech to collaborate with Saul Tukulski's team at Cornell, which had already been in existence for some years, in order to do simulations of gravitational wave sources, especially initially black hole collisions. So this is from one of the early simulations. You're going to see three ways of depicting what's going on. The two black holes against a dark blue sky up here. The other black hole is off the screen. These are non-spinning black holes, very simple Schwarzschild black holes, identical masses. Here you see a sort of an embedding diagram showing the spatial curvature and then the so-called, and color-coded by the lapse function, the slowing of time, and with arrows showing the so-called shift function, the generalization of this dragging of inertial frames into motion. Down at the bottom you see the emitted gravitational waveform, very simple in this case of non-spinning equal mass black holes in a circular orbit. And so you can watch it go around and it gets boring after a while, so we will jump, just pull over to somewhere around here in the waveform if you watch. Okay, here's the jump. Now they're going to merge. We'll pause the movie as they merge so you can admire the merger, and then we will let it go and watch the black hole, the merged black hole ring down. So this is one of the early simulations, and it was very exciting to see this. The movie was made by Harold Pfeiffer, who's now a young faculty member at Canadian Institute for Theoretical Astrophysics. But there's a problem with that visualization, and most all the visualizations anybody's ever done of black hole mergers. They depict much too little of the space-time geometry. And so you can't look at those simulations and really understand geometrodynamics at all. And so this was a puzzle that some students and former students and postdocs of mine and I got together and devised a way to do better visualizations that teach you a lot more. And so there's a paper back in 2011 that laid out the ideas. The challenge that we gave an answer to is how do you visualize the Riemann curvature tensor. In general relativity, the Riemann curvature tensor is the entity, mathematically, that describes the curvature of space-time. It actually describes also the tidal fields, the tidal forces, such as the tidal force of the moon that raises the tides on the Earth. It describes what's called differential frame dragging, how this dragging of space into motion differs from one place to another to another. And so let me begin with a baby step in discussing this. Let's take a black hole. It's a spinning black hole. As it spins, it drags space into motion near the poles, fast near the poles, slow or farther away. And we'll place a person here, either hanging or falling in. It doesn't matter. It turns out that the thing I'm going to describe is completely independent of the speed of motion of this person. It's an aspect of the space-time curvature that is what we call boost invariant in technical language. This person has two gyroscopes, one on her head and the other on her feet. And she measures the angular velocity of the gyroscope at her feet relative to the angular velocity of the gyroscope at her head. So it's a differential angular velocity. It's how fast her feet are twisting, or a gyroscope at her feet is twisting, as seen by her head. Turns out, if you look at it mathematically, if we look up from her feet and see what the angular velocity of her head is, as seen by her feet, it's identically the same thing. And it'll be if it's clockwise, it is clockwise or counterclockwise at the North Pole. Whether you're looking down at your feet or your feet are looking up at your head, it's counterclockwise. And so this angular velocity, differential angular velocity divided by this woman's height is what we call the horizon vorticity, taking a word from fluid mechanics, of course. It describes the twist of space associated with the dragging of space into motion. And at the South Pole, and that's a clockwise twist. At the South Pole, there's a counterclockwise twist. And so I'm going to show you film clips of merging black holes where I will put onto the horizon of the black hole the horizon of vorticity. And where you see red, it has some strong clockwise twist of space. And where it's blue, you have some strong counterclockwise twist of space. Now, let me get a little more technical now, because I want to describe also what's going on outside these black holes as they merge. And so I'm going to do a little mathematics, some of it already familiar. And in order to discuss electric and magnetic fields, you have to split space-time into space plus time. Even in flat space, you begin with an electromagnetic field tensor in special relativity, and you have to choose an inertial reference frame before you get the electric field and the magnetic field out as components of that. So in curved space-time, you have to choose a space-like hypersurface, which is the analog of an inertial reference frame. The electromagnetic field tensor then decomposes into an electric field and a magnetic field, and we then visualize those by field lines. For example, the electric field lines between a pair of opposite charges, those dipole field lines, or the magnetic dipole field lines around the Earth. We're all familiar with that, and all familiar with the power of electric and magnetic field lines as concepts in order to get a heuristic, intuitive understanding of what goes on in electromagnetic theory and experiment. Similarly, when you do split space-time into space plus time, the Riemann tensor decomposes into two pieces, something that is sometimes called the electric part, the analog of the electric field, and the magnetic part, the analog of the magnetic field. These are not vectors, though, as you have in electromagnetism. They are second-rank symmetric trace-free tensors in vacuum. I'm only going to talk about vacuum. So they're second-rank tensors, they're symmetric, they're trace-free. So they're like a matrix that is symmetric and trace-free. The electric part, it really describes the tidal field. And the moon's tidal field that raises the tides on the Earth and the sun's tidal field that raises tides on the Earth, they are described in precisely this way, even in Newtonian physics, by this kind of a field. In Newtonian physics, they are the double gradient of the Newtonian potential, or the first gradient of the gravitational acceleration. The magnetic part is described as we call the frame drag field, and it describes differential frame dragging, and in just the manner that I was describing before. And you can go in and read our papers, or there's a textbook by Roger Blanford and me online that is in press that has some GR chapters in it that discusses this pedagogically. We visualize then these two fields by a network of field lines such as this thing, which I will describe in a few minutes. And these are the tools for visualizing what's going on in a collision of a pair of black holes and beginning to get a real handle on geometrodynamics. So vortex lines and their vorticities. For the frame drag field, the integral curve of an eigenvector field n is called a vortex line. The eigenvalue is its vorticity. So let me go back a little more slowly. You take this symmetric trace-free tensor. It has three eigenvectors. They're eigenvector fields because the tensor changes from location to location. You pick a particular eigenvector field and you then move along the eigenvector field here from tail to tip, then grab the vector there, tail to tip, and you build a curve just following those eigenvectors. And the eigenvalue, if n is the eigenvector, the eigenvalue bnn is what we call the vorticity or the frame drag vorticity. And so that's really what I was talking about, was the frame drag vorticity of this field at the horizon for the eigenvector that's coming out orthogonal of the horizon. And so here is a set of vortex lines. Here is this person that we have out here in space outside the black hole. Her body is oriented along this vortex line. It's a blue vortex line. It has positive vorticity. M is the eigenvector field along that line. BMM is positive. She feels a clockwise differential frame dragging difference between the rotation rate of gyroscopes at her feet and her head that's clockwise. And this woman down here along this red vortex line sees a vorticity that is negative. She sees a counterclockwise vorticity. So she would feel, in some sense, her body twisted in a counterclockwise way if her body is attached to gyroscopes, whereas this one would feel her body twisted in a clockwise way. And interestingly, these counterclockwise vortex lines, they emerge from the north polar regions, swing around the black hole, come back and descend back into the north polar regions. And the clockwise vortex lines emerge from the south pole, swing around, and go back up into the south pole. And then there's another set. There are three eigenvectors for a symmetric tensor, 3 by 3 tensor. So there's another set, and these are vortex lines that twist around and around in a spiral, emerging from the horizon and going off in a twisting pattern out into interstellar or interpolar space. And so that's the Curvature, but that's the Curvature in a form that most of you have never seen before, and it really depicts what's going on with the frame drag field. And so this was really sort of an eye-opener for me when we identified how to do this. The regions where we have very strong vorticity, very large twisting of space, we call vortexes or vortices. So a vortex is a collection of vortex lines with large vorticities. And so there's a red vortex, a counterclockwise vortex coming out of the north polar regions, a blue or clockwise vortex coming out of the south polar regions. Now let me talk about collision of two black holes at last. And I'm going to talk about the collision of let me just check on how I'm doing on time. Okay. I have collision of two black holes head-on with transverse spin. So this is painted red on the top, so that's a counterclockwise vortex coming out of the north pole, a clockwise vortex out of the south pole. Here the clockwise is coming out of the north pole, the counterclockwise out of the south pole. Now we do not yet have movies of how the vortex lines evolve. You can ask me in the question period why not, and I will confess what the problem is. But we expect to have those soon. And so I'm just going to, as we watch the dynamics, I'll either show you stills of vortex lines, or I will show you the evolution of the horizon vorticity. So here are these two black holes. They're heading head-on into merger they merge, you now have one black hole. This is the horizon, the absolute event horizon. The boundary between what can and cannot, where if you're inside there, nothing can get out. If you're outside there, things can get out, information can get out. We began with two vortexes attached to this hole, two attached to that hole. The holes merge. We now have four vortexes attached to the same hole. That's not natural. A quiescent black hole only has two, and so somehow this black hole has to change its whole its structure, its vortex structure, after this merger has occurred. But the important thing is that in this merger, these vortexes robustly retain their individuality. And so we will watch what they do then following this moment of merger. And so here's a movie of the merger. And so I'll let you just watch. Remember, this is blue on the right and red on the left. Now it's red on the right. Now it's blue on the right. Now it's red on the right. Now it's blue on the right. And it's dying out. In some sense, these vortexes are fighting with each other, strangling each other. I don't know what words you want to use. They're exchanging vorticity in the process. So what was originally a blue vortex becomes a red vortex, then it becomes a blue vortex, and it oscillates. In more detail, if you look at stills of the vortex lines, a particular moment when it's strong blue and strong red, what has happened is that the vortex lines that were red, that were sticking out up here, and red ones that are on the back, there are two red ones and two blue ones. You see a red and blue on the front, and then the red and blue on the back. Those vortex lines have reconnected. The red vortex lines that when this was one black hole went out, wrapped around, and came back into the same region as it started. It's reconnected onto the vortex lines that were coming from the other black hole, and so you now have a vortex tube that is going out, around, and coming back into the other side, the polar opposite side of the black hole. And blue coming out from here, going around, coming into the polar opposite side. So once the merger occurs, there's a reconnection of these vortex lines in that manner. And what is really interesting is that as this oscillation occurs, you have these green epochs, which just means that there are no vortex lines sticking through the horizon at all. So these vortex lines have to pop off the horizon as that oscillation occurs. And what they will do is they'll pop off the horizon, and then they will attach onto themselves, and you get a vortex ring. In fact, a sequence of vortex rings, rather like smoke rings, that go traveling out from the merged black hole into interstellar space. Oscillation after oscillation, producing weaker and weaker vortex rings going into interstellar space. I mean, this is geometrodynamics. This is the nonlinear dynamics of current space-time. We had no idea that this happened until we did these simulations and had these visualization tools in the last several years. Now, just as if you take a magnetic field and you move it, it generates an electric field. Similarly, you take these vortex lines and move them, and they generate Tendex lines, that is, field lines associated with a tidal field. The frame drag field and the tidal field have a relationship similar to the magnetic field and the electric field. And so as these vortex tubes go flying out, they generate, wrapped around them, Tendex lines, stretching Tendex lines that are going around, in this case, around the long part of this torus, and squeezing Tendex lines going around the short ring. And the next torus is going to have the Tendex lines and the vortex lines reversed, and to go back and forth, oscillating back and forth. And these Tendex lines are the integral curves of the eigenvectors of the tidal field, the other part of the Riemann curvature tensor. And so once this ring gets far away from the merged black hole, it locally looks just like a flat plane wave. And you have the vortex lines and Tendex lines. Here are the vortex lines, there are the Tendex lines. They really should be superimposed on top of each other. I've just split them apart. And so you have a stretching, in this case along the red lines, and a squeezing along the green lines. That's a gravitational wave. And these are gravitational waves. These will travel out through interstellar space, come to the Earth, carrying the pattern of stretch and squeeze, the gravitational waveforms that were produced in the merger, be detected by LIGO, monitored by LIGO. We will go in, look at those waveforms, and we'll go back to the simulations, and we'll try to figure out just what was going on in the simulations. What kind of a pair of black holes was it that generated this, and what was the geometrodynamics that generated this? More realistically, instead of head-on collisions, we have black holes that orbit around each other. And in this case, I'll just very quickly show you what happens. In this case, instead of getting vortex rings, you get spiral arms, which is not surprising. You have these vortex lines that stick out. And the merged black hole has 4 spiral arms, 2 blue ones and 2 red ones. But then from the orbital angular momentum that you had, you now have a spin of that black hole that is orthogonal to this plane, and so you have another pair of vortex lines sticking out orthogonal to this plane. So you really have 6 vortices sticking out, basically, 6 pairs of vortex lines. And this is at late times, just from black hole perturbation theory, in the equatorial plane. This is the kind of pattern that you have for the vortex lines. 2 sets of orthogonal vortex lines. The third vortex lines are going through that plane up toward us. And if you think about it, what's really going on in here is that the gravitational waves, which are these spiral patterns, they are being generated by vortexes or vortices that are sticking out of the black hole, attached to the black hole, and that are turning around and around. Inside this yellow dotted curve is the near zone. And in that near zone, you have the same kind of vortex structure as you would have around these 2 original black holes. You just have vortexes that are sticking out. They are tumbling. But then you get outside the yellow region, you're in the wave zone, and the vortexes swing back in a spiral pattern and become gravitational waves. Okay. So I want to go away from that for a moment and talk about the real power, the physical power of vortexes and tendexes. I'm going to show you a simulation of a black hole tearing a neutron star apart. The black hole is spinning around this axis. That's its spin axis. It's off at an angle. The neutron star is orbiting in a horizontal plane. And so the spin axis of the black hole is not orthogonal to the orbital plane. The black hole is 3 times heavier than the neutron star, and so it turns out to be just a little bit bigger in the simulation than the neutron star. The black hole spins at half the maximum rate that is allowed for a black hole around that red axis. What you're going to see is the tidal field from the black hole, the tendex lines or the tendices, will reach out, grab hold of the neutron star and tear it apart. 1 solar mass of nuclear material compacted into a region about the size of central Melbourne. It's going to be torn apart by the tendexes or the tendices that stick out from the black hole. And once it's torn apart, the nuclear matter is going to interact with the vortices. And it's going to get thrown up into the plane orthogonal to the spin by the vortices. And this is enormous power to take a solar mass of nuclear material and do that. And that's what you will see happen. That little plane you see is just the original orbital plane. You wind up in this particular case with, I've forgotten the number, something like 90% of the nuclear matter goes down the black hole and 10% goes into an accretion disk around the black hole. And this is the accretion disk that's in the process of forming. This is a simulation by the Cornell part of the SXS collaboration done a few years ago. But this is by way of motivating what's called multi-messenger astronomy. We have the gravitational waves from the in-spiral and the tidal disruption of the neutron star. You've got gamma rays and neutrinos coming off from this neutron star as it's torn apart and from the accretion disk afterwards, and then you have light, you'll have radio waves from magnetic fields that are all tied up in all of this. And it's just very exciting to do this kind of multi-messenger astronomy, which is a major issue for the near future of LIGO. So let me just say a few words about gravitational waves as a probe of geometrodynamics. The gravitational wave observations, well, just to remind you that there are ground-based interferometers that can look for gravitational waves from black holes that have masses from 2 solar masses to 1,000 solar masses. Space-based interferometers we hope will fly within the next 2 decades. See black hole binaries merging from 10,000 to 10 million solar masses. And then pulsar timing arrays, which are a very big thing in Australia. And I'm rather ashamed of the US for having been so slow to get onto this effort. Pulsar timing arrays, black hole mergers 100 million to 10 billion solar masses. I'm focusing on the ground-based interferometers. Gravitational wave comes in. Here are the 10-dex lines from this gravitational wave. They stretch along the red 10-dex lines, which stretches these mirrors hanging from overhead supports apart. Squeeze those mirrors together, and then it oscillates back and forth. And of course, we use laser interferometry to monitor that. Delta L, the change in separation divided by L, is called the gravitational wave strain or the gravitational wave field. It's dimensionless. And that is the quantity that we compute in our simulations. There are really 2 gravitational waveforms, one for stretch and squeeze along this pair of axes, the other axes twisted by 45 degrees relative to the original pair. So as for electromagnetic waves, here's also gravitational waves, there are 2 waveforms. Here is a waveform, the 2 waveforms produced by basically a generic binary black hole. We have here a 60 solar mass black hole with a spin of 91% of the maximum. Initial spin axis is in that direction. 10 solar mass black hole, spin 30% of the maximum, spins in that direction. This is the direction to Earth, and these are the waveforms that you would see in that direction. But as you can see, there are a lot of parameters in here. There are 2 masses. There are 3 components of spin for 2 black holes. So there are a total of 2 plus 3 plus 3, 8 parameters in this problem in terms of the waveform that's going to be seen at Earth. And then there's the parameter for the direction to Earth, which gives you 2 more. And so you've got 10 parameters altogether. So there's a huge, huge richness in gravitational waveforms and a huge, huge challenge to generate the waveforms for data analysis. And so the SXS team and other people who do numerical relativity are doing similar things, but we are now carrying out 1,000 simulations to underpin the dictionary to be used in LIGO data analysis. The waveforms that are used in searches for gravitational waves today in the initial LIGO, in the advanced LIGO searches for merging binary black holes are based on these simulations and other simulations by other research groups. So they are numerical relativity waveforms. And so these are just examples of different binary black holes that we simulated early on in this effort. We're now carrying out 1,000 simulations. 1,000 is our goal by summer of 2017 to underpin the dictionary. 400 are finished, 403 are finished, 100 are underway, due to be completed by the end of this year. So by January, we should have a little over 500 simulations under our belts. I don't do these simulations. I'm sort of a figurehead who is one of the co-investigators that has overseen this through many years, but I don't do this. All I've done is the same thing here as I did in LIGO, is provide some scientific motivation for what's going on. Yeah, most of you are all well aware of this. There have been talks here at Monash in recent months and years about it, but just to remind you of numbers, the gravitational wave field from these kinds of sources realistically is less than or of order 10 to the minus 21. You have arm lengths in LIGO of 4 kilometers. That means delta L is less than or of order 4 times 10 to the minus 16 centimeters. So you need a noise level, say 10 times below this. And that corresponds to being able to monitor the motions of mirrors at a level of 1/10,000th the diameter of the nucleus of an atom over a separation of 4 kilometers. And this is what this fabulous team of experimenters is doing. It's just unbelievable what they've achieved. And of course, there's a network of ground-based gravity wave interferometers. The moment the advanced LIGO is the only thing that is operating together with a test bed that we have used for technology development in Hanover, Germany. And so there's 2 LIGO detectors in green, the Geo test bed detector in Germany. Virgo will come online in Pisa, Italy within 2 years. A detector is now called CAGRA. I don't know how, I don't have this changed, in Japan. And then LIGO India, which is supposed to be LIGO Australia. I wish it had been LIGO Australia. We would have had a better network if it were Australia. But it's due to be in India, and that's probably more like 4 years away, 3 or 4 years away. The network is needed for confidence that what you're seeing is real, for extracting the waveforms, and for determining the direction of the source by triangulation, so you can do multi-messenger astronomy, compare with electromagnetic signals. LIGO is, of course, a collaboration of 900 scientists at 75 institutions, 14 nations, including the US, Australia, UK, Germany, and so forth. And just for him, from a historical point of view, we made our proposal to construct LIGO in 1989, and we said at that time it would be a 2-step strategy. Initial interferometers at a sensitivity where it is plausible to see waves, but we probably wouldn't. You'd have to be lucky. And then advanced interferometers at a sensitivity where we would be likely to see waves from a variety of sources. We had to do it in 2 steps because it was much too big a technological leap to do it in 1 step, to get from where we were in the 1980s to where we actually are today. It was much too big a step to do all at once. And this has paid off. The achievements of this team with the advanced interferometer are just phenomenal, as I will show you in just a moment. The initial interferometers were built and then operated from 2005 to 2010. They were capable of seeing 2 black holes with masses of 10 solar masses out to 300 million light years. None were seen. Interesting limits were placed on this. And of course, searches were done for a variety of other sources that I won't go into: supernovae, binary neutron stars, cosmic strings. The advanced interferometers installation began in 2010. The first observational search, it's called the 01 search, began 1 month ago. It's currently at about 1/3 of its design sensitivity, capable today of seeing binary black holes of 10 solar masses out to 1 billion light years. That's 1/10 of the way to the edge of the observable universe. That's what is being done today. At design sensitivity, you'll see roughly 4 times farther. So out between 1/3 and half the distance to the edge of the observable universe. Design sensitivity is expected to be reached by 2019. At that, the estimates for event rates for binary black holes are between 3 a year and 1 a day with the advanced instruments. If it's 1 a day with the advanced instruments, then with the instruments that we have operating today, the rate should be roughly 1/30th, 1/50th of that. And so it's like 1 every couple of months, something like that. Is that right? Yeah, something like that. Anyway, it's one a month or so if we're lucky, with the current instruments. So we could be seeing gravitational waves in the 01 search. It would be very surprising if we're not doing a lot of science by the time we were at design sensitivity. Noise curves. If you look at the axes, this is 10 hertz up to 1,000 hertz, going up toward 10,000 hertz. A very broadband instrument. The noise is what's called the square root of the spectral density. It's this H field per root hertz, and that's the way noise behaves. You multiply by the square root of a bandwidth in which you're searching for a wave in order to see what H is, what the strength of the wave of the noise actually is. So down here you see a bit below 10 to the minus 23, multiply by the square root of 100 hertz, you're at 10 to the minus 22. Noise level at 10 to the minus 22 in order to see gravitational waves at 10 to the minus 21 with a good, healthy signal-to-noise ratio. It's interesting to compare this. So these are the noise curves for the two instruments, one in Livingston, Louisiana, the other in Hanford, Washington. This is the GEO testbed instrument. Of course, not nearly as good. It's a much shorter interferometer, and it was just developed for technology development, not really for searching. But it's interesting to compare with initial LIGO. That was the noise curve actually achieved with the initial interferometers. And down at the bottom of the noise curve, we're currently, the LIGO team, advanced LIGO, is 3 times better than the initial detectors. Up at high frequencies, it's 30 times better. You cube this in order to get event rate. 3 cubed is about 30. 30 cubed is about 30,000 times higher event rate up at high frequencies. Of course, 30,000 times 0 is still 0. I won't comment on that. But the source rate estimates make us really very optimistic about what we're going to see. And down at low frequencies, 1,000-fold improvement. So that's very impressive. Another impressive thing is in 2013, the best experts in LIGO made an estimate of where we would be once we had turned on in terms of sensitivity. In 2015, we would be somewhere in the blue region, 2016 to 17 in the green region, 2017 to 18 in the red region, 2019 at design sensitivity. It's a really very complex process. These are extremely complex instruments, and bringing them to design sensitivity is a very complex and major effort. So where are we now? That's the 01 search. We're actually down into the green region on a little tiny bit of this, and well deep into the blue region everywhere except at the very, very lowest of frequencies. It's really very impressive what this team has achieved in terms of sensitivity. So that's where things are today. First search, we're 1 month into it. But just to remind you, at this level, binary black holes of 10 solar masses, 1 billion light years is how far we should see. That level, 4 billion light years. Plus all the other sources, neutron stars, the engines for gamma ray bursts, supernovae, cosmic strings, black holes tearing neutron stars apart. It's really an exciting time. For me, as a fundamental physicist, another exciting aspect of this is that in advanced LIGO, we are monitoring the motions of 40 kilogram mirrors to delta L about 10 to the minus 17 centimeters, which is the half width of the Schrodinger wave function for the position of one of these 40 kilogram mirrors. So we deal with our mirrors as 40 kilogram quantum mechanical particles when we analyze the noise in LIGO. This is called quantum noise. It's a mixture of shot noise and radiation pressure noise. And this is, for me, one of the most interesting aspects of LIGO, that for the first time in LIGO, human beings are on the verge, and will be at design sensitivity, of seeing human-sized objects, 40 kilogram objects, behave quantum mechanically. And the quantum non-demolition that Yuri referred to, the standard quantum limit, this all refers to this business. We have had to build into these instruments the capability of collecting data and analyzing the data in a way that takes account of the quantum behavior of 40 kilogram particles. And it's really very interesting to me as a fundamental physicist. For the first time humans see human-sized objects behave quantum mechanically. Quantum non-demolition technology has been developed to deal with this. And it is a branch of quantum information science. Other branches include quantum cryptography, quantum computers. So I'm going to quit just by listing other arenas for geometrodynamics. If I'd had time, I would have talked about them. I thought it was better to linger on this, which is the most exciting current stuff. But I do want to alert you to the fact that we do know a fair amount about geometrodynamics in very special other circumstances, things that we have learned through combinations of early numerical simulations and very sophisticated and clever analytical work. We understand the space-time dynamics near singularities, cosmological singularities, singularities inside black holes, and it's very rich dynamics of the Riemann tensor. It's dynamics that turns out for certain generic singularities to be characterized by chaotic mathematical maps, the kinds of mathematical maps that people study in chaos theory. And so you see chaotic maps coming out of Einstein's equations and controlling near a singularity the dynamics of the space-time curvature. Analyses have been done, computer simulations of the implosion of gravitational waves that have enough energy in them to form a black hole. Just ingoing waves make a black hole. If you turn down the strength of the waves a little bit, you don't get a black hole. And right on the edge between waves that are strong enough to make a black hole and not strong enough, you see really interesting dynamical behavior. You see phenomena very much like those in a phase transition in condensed matter physics. You see critical behavior. You see scaling laws like those in a phase transition. And you see gravitational waves coming off from this object that is trying to make a black hole that have very interesting self-similar patterns, discretely self-similar patterns. And so a lot has been learned in this venue also about geometrodynamics. And in higher dimensions, if you have a space-time that has one higher dimension, and maybe we have one higher dimension. If you went to see Interstellar, there's a claim there's one higher dimension. So if there are really 5 dimensions, then instead of black holes, you can have black strings. They're black holes that have a translation symmetry along them. And Franz Pretorius and Louis Lehner have analyzed the dynamics of black strings, and it's unbelievable dynamics that's epitomized by the formation of black holes connected by thin strings in a hierarchical fashion that is just amazing to see coming out of the simulations. And so I'm going to stop at that. Instead of talking about those, I'll answer a few questions, but just I want to conclude by saying that for me, having been fascinated through the teachings, the personal exhortations from Johnny Wheeler, back when I was his student more than half a century ago, to see insights about geometrodynamics really coming out of this combination of numerical simulations, soon to be from gravitational wave observations, and then analytic work that is stimulated by what you see in the numerical simulations. You then go in and try to understand analytically what's going on. It's really an exciting time in what is really just the nascent very beginning of this new field of geometrodynamics, a field that we tried to get going in the 1960s and failed, but finally it's taking off. Thanks.
Thank you. Since it's non-linear, and you mentioned chaotic behaviour, how can you be sure that the solutions that you derive are unique or, aren't super sensitive to?
So you always have that issue when you're dealing with chaotic maps. And so what has been the place where we see chaos is in the singularity, is the evolution of the Riemann tensor, the tidal field, the frame drag field, as you approach this singularity. And this beautiful analytic work done by Lifshitz, Kalatnikov, and Belinsky in the Soviet Union in the late 60s and early 70s showed that they argued that the pattern that you get of oscillations, the pattern, in the language I was using, the pattern of oscillation of the eigenvalues of the frame drag field and the tidal field is governed by a certain chaotic map. There was a lot of skepticism in the West. People in the West tended to demand higher levels of rigor, and these were not rigorous analyses. But people, particularly David Garfinkel at Oakland University, have gone in and they've done simulations now in recent years on computers, and they've seen just this behavior in generic situations near a space-like singularity. And so it's proved analytically with moderate rigor and seen numerically that you have these chaotic maps with extreme sensitivity to initial conditions. And so it's true, you're not going to predict what happens after the 12th iteration of this map, after 12 sets of oscillations. You're not going to predict precisely where you're going to be, but you can predict the whole pattern of oscillations. And that's the way it is generally with chaotic maps.
So I have a very simple question. Looks like in the head-on collision of two black holes, it seems like you start off with two Kerr black holes, and then you create a Schwarzschild black hole. Is that right?
That's correct, because we chose, the team I work with chose that the two initial black holes had opposite spins and were identical in spin and mass. We just chose that because that was a simple case to analyze. And we went fishing to see what would happen, and we got this very interesting result. But it is particularly simple because you wind up with a Schwarzschild black hole in the end. Yes.
So what prevents you to show the vortex lines on those?
So the problem is this, and it's a problem that you also have in making movies of electric and magnetic field lines. At any given moment, you can lay down the pattern of field lines. But how do you map one field line into another particular field line at the next time step? And there's some amount of arbitrariness in that. There's no arbitrariness if you're doing perfect magnetohydrodynamics. Then the field lines are frozen into the fluid, and the motion of the fluid tells you how to map the field lines from one moment to another. But in generic situations, there is a fair amount of arbitrariness in how you map one field line to another. And so that means that one of the things that your eye catches the most is the motion of the field lines, and there's arbitrariness in the motion of the field lines. The pattern is fixed, but the motion is not. And so we have not yet reached a good conclusion about how to do this mapping from one frame to another as you step along in time. What we are currently doing and just trying out is those field lines that come from merging black holes that extend out into the wave zone. We just move them out radially at the speed of light because we know that that's how the energy is flowing. And then each field line is uniquely determined all the way back down into the interior, and it goes wherever it goes and can be followed. And so we're just exploring that at the moment to see how that works out. But it's still early days in this. It's been, I have to confess that I was a driving force for this, and I got distracted by making a movie for a couple of years. And I'm now back on it and really pushing it hard.
If Einstein's theory is only approximate in the strong field limit, would LIGO give you indications of that?
What makes you think it's only approximate in a strong field limit?
Well, I don't know, but we know it's quite good in the weak field limit.
So that, I mean, that's not a fair remark, since I spent a big piece of my early career asking questions: how do you prove how good it is in the strong field limit? And so one of the nice things about black hole binaries and neutron star binaries is that as they spiral in, the nonlinear effects get stronger and stronger in a very gradual sort of a way. And so in the waveform, step by step, you can see what's called the first post-Newtonian corrections come up. These are the things that are basically quadratic in the strength of the Newtonian gravitational field. And then the second post-Newtonian come up and get strong, and then the 2.5 post-Newtonian, then the 3rd post-Newtonian, and so forth. And so in the waveforms, we can see the gradual development of the fully nonlinear, the gravitational. When I talk about this, I'm talking about the post-Newtonian, 1st post-Newtonian, 2nd, 3rd post-Newtonian in the orbital motion, in the interior dynamics of the binary. And so and that shows up in the waveforms. And so in the waveform, you can see the influence of the 1st post-Newtonian corrections to gravity in the interior. And then the 2nd, then 2.5, 3, 3.5. And so one of the plans with LIGO data analysis is to map that out observationally and see whether the pattern follows precisely what GR says it would. So that's one answer. Another answer is just the gravitational waveforms from merging black holes. This is the ultimate geometrodynamical, or at least one of the ultimate geometrodynamical venues. And there's a huge amount of waveform space that does not correspond to what you see in merging black holes. Even though there are lots of parameters, it's still a tiny piece of the potential waveform space. And so you look at these waveforms, we will look at these waveforms as LIGO gets better and better, and you get more and more accurate waveforms, and see whether they really follow the predictions of the numerical simulations or not. So this, in fact, is one of the goals, is to do tests of general relativity in the strong field situation. Yeah.
Could you please comment on intermediate mass black holes? Where are they?
Well, are there any?
Are there any?
So LIGO can see, advanced LIGO should be able to see black holes up to about 1,000 solar masses, 500 solar masses, something like that. And so it will be simply very interesting to do the demography of black hole binaries and see what is the distribution of masses in merging binary black holes. And it's conceivable that that's where we will first see our absolutely firm evidence for intermediate mass black holes and see how common they are in the universe, at least in binaries. And so this again is one of the science goals for LIGO that we spelled out in our proposal for advanced LIGO. This is one of the things we would do.
So you showed us simulations of merging black holes. Have you observed simulations of the opposite? To take a black hole and increase its spin, would it split into two?
So general relativity theory says it can't. And it would be wonderful if we could see it happen. Because that would be a proof that there's something wrong with general relativity. I think we're close-minded enough about this that nobody has developed templates to look for something like that. And I could imagine at some point in the future when things calm down in this field after the first few years of doing science on things that you think have some chance of happening, that somebody will go in and do searches for that kind of thing. But general relativity insists it never happens.
So I guess my question then relates to something you mentioned earlier, which is the maximum spin rate of a black hole. I'm not familiar with the field,
yeah. So the story is this. Suppose that you have a black hole that's spinning very close to the maximum. You want to spin it up above the maximum by whatever means. So for example, you throw particles into it. And if it's spinning in this direction, you throw particles in going in that direction so they'll be captured and spin it up faster. But when it's spinning very close to the maximum, the cross-section to capture particles that are going against the spin, it becomes enormous. The cross-section to capture particles along in this direction of spin goes to zero. And basically, it becomes impossible to spin it up. You can do little calculations using perturbation theory and see you just can't get a particle that is carrying enough angular momentum, the right kind of angular momentum in to spin it up. It won't go into the black hole. The black hole rejects it. And it quickly and easily captures particles that will spin it back down. And so I looked at this issue together with a student Don Page many, many years ago in the early 1970s. And we imagine then you have a black hole that's in an astrophysical environment, say at the center of an accretion disk. It's being spun up by gas from the disk, being spun down, not by the gas from the disk, because that's going in the wrong direction, just by the radiation that comes off the disk and gets captured really easily when it's spinning fast. And it appeared to us, and I think this still holds true, that things, the black hole will tend to buffer into a spin of 0.998 times the maximum possible. And it strongly rejects anything you try to do to it to make it spin much faster than that. And it happily accepts stuff if it's well below 0.998.
This didn't seem to stop you in Interstellar of giving your black hole a much higher spin.
Well, I had the problem in Interstellar. I had a collaborator named Christopher Nolan. and Chris said to me in one of our early discussions, he said, I want 1 hour on Miller's planet to be 7 years back on Earth. And I told him that's impossible. He already knew me well enough, and his brother knew me even better, to say, go think about it. Go do a real calculation. So I was sure it was impossible. And so I did. I went home, I did a real calculation overnight and discovered it is possible in principle. But you're in this domain that you can have a planet in orbit around a black hole that's spinning so fast that on the planet you have that very, very high loss of time, slowing of time. But it requires a black hole that has a spin of something like 13 nines, something like 13 nines, which in any natural astrophysical environment just won't happen. But in principle, it's possible. If somehow this black hole were protected, it could happen. In reality, no. And so this is, if you look in my book, The Science of Interstellar, at the back, not in the people index, this is sort of hidden. It's for the cognoscenti. If you look in the back, in the subject index under Christopher Nolan, you'll find a list of pages for all of the compromises, science compromises that were made in this film. And there are a lot of them, but not in the point that they violate physical law, just in the point that they stretch things a little farther than an astrophysicist would be comfortable with.
Yeah, so I'm sorry to take this back to the technical physics, but I was completely intrigued by the split of the Riemann curvature into the electric and magnetic components. And I suppose, you know, in the far zone, then it's very easy to expect that the tidal forces dominate. But is there any way of sort of trying to measure the magnetic component in the near zone, for example? I mean, I know in pulsar timing arrays they do talk about sometimes being able, potentially being able to measure near field effects.
I don't know, but I think it would be worth putting some real thought into it. I mean, just in the context of the black hole tearing apart the neutron star, you see how strong that frame drag field can be. But I've never really thought about how it might show up in observations like that.
Is it possible you'll have a problem with crowding too many sources interfering with each other?
Boy, we should be so lucky.
Yeah, well, you know, I think.
So with a space-based gravity wave detector, LISA, a space-based analog of LIGO, this will happen. You'll have tens of thousands of sources on at the same time. And it's like tuning radio stations. If you have several hundred radio stations or even TV channels, you can readily tune in on one or another through, quote, data analysis. Well, through hardware, but and twisting a knob. But it's similarly in this field, we're doing the analog in some sense of audio physics. We're dealing with waveforms operating in the time domain, very broad band signals in the time domain. And so if you're going to even find these things when there's a lot of crowding, you've got to know the waveforms in advance, or enough characteristics of the waveforms in advance that you can zero in on them. But that is the strategy. And that's again why theoretical understanding in advance is so important. And also why what for me is actually the most exciting aspect of this field, discovering completely unexpected things, may be difficult. Because if the completely unexpected things have waveforms that are less than 10 or 20 cycles, okay, that can be found without knowing the waveforms in advance. There are clever techniques by the so-called burst search group that in LIGO that have been developed that are really good at finding short, unexpected, completely unpredicted waveform signals. But if you've got 100 cycles or 1,000 cycles, you cannot dig down into the noise without a lot of prior guidance. And I do expect that when the field becomes mature, that's going to be a big issue in looking for unknown news kinds of sources. How do we do it? How do we dig into the noise? In this case, it's not separating signals out from each other. In LIGO, we expect we'll pretty much always be separating them from noise. But separating them from each other is not all that different from separating them from noise. It's the same problem, more or less.
We have time for 2 more questions.
Could LIGO be potentially used to discern between a black hole and a white hole?
A black hole and a white hole. So a white hole is a hypothetical object that is a piece of the Big Bang that didn't go bang yet, in some sense. It says a black hole is an object into which stuff can fall and it can never come out. White hole is an object, stuff can come out of it and never fall in. But there are analyses, computations that show that if you have a white hole in the real universe, it will accrete matter, even just cosmic microwave background, onto it. And that will create a black hole horizon around the white hole and basically hide the white hole from the external universe. And so this is one of those things like splitting a black hole apart. That I don't think there are any white holes out there because they've all been converted into black holes, and so I've not thought about how to search for them. And maybe somebody who's less closed-minded than me will figure out how to search for them and think it through and change how we view all of this. But at the present time, I know of no work on this whatsoever, and I think the reason is that the general relativists were convinced by Douglas Airdley back in the 1970s that all white holes will convert into black holes in a few dynamical timescales.
Last question.
In terms of needing to know the gravitational waveforms in advance, does a simulation suite of 1,000 in the 8-dimensional parameter space, is that sufficient?
So that's a crude way of saying what the challenge is, 1,000. We picked the number 1,000 sort of out of the air by the seat of our pants maybe 6 years ago. And it has held up since. The key issue is that you want to do targeted simulations in such a way as to build an analytical model that covers the waveform space that's informed by some set of simulations that are very carefully placed in parameter space. So they give you all the data you need to cover the whole function space of the waveforms. And so there is a technique for doing this called reduced basis modeling, something like that. Is that right, Frey? Reduced order modeling. I'm not close to this like Eric is. Reduced order modeling that's been developed by Chad Hanna, or Chad Galley and others. And I've not followed the details of the development, but it is somewhat like in a vector space, picking an initial basis vector, then a second basis vector orthogonal to that, then a third one orthogonal to that, and just building up a set of basis vectors that are going to be able to cover your vector space. And so in the last several years, the techniques for doing that have been developed for dealing with these waveform spaces. And are now sufficiently mature that the guys that are doing this are now informing these simulations in that way and beginning to choose which simulations to do in order to build then this analytical model that will cover the waveform space to the accuracy required for gravity wave searches. That will not be adequate accuracy as advanced LIGO becomes mature for the data analysis, for extracting parameters. But what will then happen is you see a binary black hole that sits at this location in parameter space somewhere in some error region. And you go in and you repeat it. You do a carefully selected set of simulations to build a basis in there and build an analytical model and then get the parameters. And so the estimates that we made by the seat of our pants a few 6-8 years ago, I'm told have been more or less validated by this development of how to do it in a really systematic manner. But I'm waving my hands because I'm talking about something that I should know cold, and I don't because I've been making movies when I should have been doing this. So you have to go read Chad's paper.